So hi everyone. So last class we looked at some outline of data sciences and how it is evolving these days. So you need certain mathematical preliminaries to understand the algorithms of data sciences. So we'll cover that over a couple of classes. So let us start with linear algebra, some elements of linear algebra. You must have done it in other courses, but I'll just do a quick recap, right, so that you can just recall the main ideas. So let's start with the definition of vector spaces. So vector space set of a set V on which two operations, addition and dot product, that are defined, called vector addition and scalar multiplication. So addition rule says if U and V, which are vectors which are inside this set, belong to this set V, then U plus V, right, is also in this set V. U plus, I mean, small v. So multiplication rule says if U is in V and A is a scalar, a real number, then A times U is also in the set V. Now, if 0 is a 0 vector, that this is a vector. So in some textbooks, they use a notation. So at some set, they use a notation of 0 with some kind of a slash cutting through. Okay, just to distinguish that it's a vector and not the scalar 0. So if 0 is at 0 vector, then A dot U is 0 if A is 0, this 0 vector. And A dot U is 0 if U is also a 0 vector. So these are other two instances of that rule. Now, if you want to go to linear combination, if V is a vector such that V is equal to some sigma AI UI, right, where U is in V and A's are all in real numbers, then the vector small v is also in the set capital V. That any linear sum of the vectors which belong to a set V, right, is also in the same set. So this is also a property of vector spaces. Now from that we can introduce the concept of linear independence. That is, so let us define this expression sigma AI UI is equal to 0, right, such that not all AIs are 0. Suppose it is possible, right? Then UI are linearly dependent. Otherwise, UI are linearly independent. So this is the definition of linear independence. So the vectors U1, U2, UN are said to be linearly independent only if the summation sigma AI UI is equal to 0 has only one trivial solution, when all the coefficients are 0. Right? So if this expression is 0, only when all the coefficients 0, then you say that the vectors U1 to the UI are linearly independent. Otherwise, they're linearly dependent. So the rank of the matrix is also related to the concept of linear dependence or independence, because a matrix is basically a bunch of vectors arranged in either a column form or a row form. So a rank of a matrix A, which is an m by n matrix of real numbers, it is the number of linearly independent rows or columns. So smaller of the RA is minimum of n or m normally, if it is a full rank matrix. All right, but actual rank could be even smaller than both m and n, even smaller than the min of m and n. Now let us define inner product and outer product. Inner product is what you also call the dot product, popularly called dot product. So if U and V are two vectors which are just n-tuples, what you know in the n-dimensional Euclidean space, Rn, right? Then U dot V is also written as U transpose V. So because U and V are now just vectors as in a bunch of numbers, all right? Then you can express them as column vectors or row vectors. And but typical convention is vector in a matrix form is a column vector. Let us stick to that convention. All right. So then U transpose V will be a scalar, because if U is right? U1, U2, etc. And small v is also V1, Vn. So U transpose V will be this, which is a scalar. But if you take UV transpose, right, then you get a matrix. You can easily work out, right? U is right. U transpose is n by 1 by n, and V is n by 1. So this is a scalar. Whereas here it is n by 1 times 1 by n. So therefore, this is a matrix of size n by n. So this is called the outer product. So we distinguish inner product from the outer product. So just examples. So if you take U is equal to the vector 1, 2, 3, and which you assume is also equal to the second vector V, then U transpose V is simply 1 square plus, hope you can see this. U transpose V is equal to 1 square plus 2 square plus 3 square. But whereas, right, sorry, UV transpose is this matrix. So now let us introduce eigenvalues. So if A is a square matrix, it doesn't have to be symmetric, it's just a square matrix, right? Then look at this equation, Ax is equal to lambda x, right? The solutions of this, so you have to find x, which can be a complex vector, and lambdas, which can also be complex numbers in general, right? So which satisfy this are said to be the eigenvalues and eigenvectors of A. So the eigenvalues can be found by solving this equation, because if we take lambda x to the left side, you have ax minus lambda x, or a minus lambda I times x is equal to 0, which means, right, this matrix must be a singular matrix. So therefore, the determinant of this is equal to 0. So this we know that from you all know this from your high school. So if you expand this, then you'll get a polynomial of a degree n in lambda. So we know that from fundamental theorem of algebra, the nth degree polynomial will have n roots always, real or complex. So for n by n matrix, you always have n roots or n eigenvalues, right? They can be real or complex. And so basically what, if you look at this expression, we'll interpret this geometrically later, the eigenvalue equation. So if Ax is equal to lambda x, so basically when you multiply a vector by the matrix A, then if that vector happens to be one of the eigenvectors, right, then that multiplication amounts to simply stretching the vector by some factor lambda. So this is what, I mean, intuitively, if you want to interpret this geometrically, this is what this equation tells us. So the eigenvectors associated with the distinct eigenvalues are linearly independent. So if so, since this is called the characteristic equation, determinant of a minus lambda, it's a polynomial in lambda, and the degree polynomial in lambda. So it will have n roots, but it's not guaranteed that all the roots are distinct, right? And the thing is, but if two eigenvalues are distinct, right, their corresponding eigenvectors are all linearly independent. So that's the theory guarantees that. So for example, take this matrix A 1, 1, 4, minus 2, right? If you calculate eigenvalues, you get 2 and minus 3. So if you plug them back into the equation and solve for x equal to lambda x, right, then you can find that V1 is 1, 1, of course, transpose, because we'll use column vectors by convention. So V2 is 1 minus 4. So you can see that these are linearly independent because the two eigenvalues are distinct. Okay, so I guess you know how to do this. So find the roots, 2 minus 3, and plug it back in here. So if you plug the, let's say 2 in here, you get 1 minus, right, plug lambda equal to 2 here, 1 minus 2 here, and minus 2 minus 2, so you get 4 here. All right, if you solve this equation, last equation, you get x1 is equal to 1, x2 is equal to 1. So that is the eigenvector. Similarly, if you plug in lambda is equal to the second eigenvalue, lambda 2 is equal to minus 3, you get a different thing. So this is a clean case, there's no problem. The problems arise when you have multiplicity of eigenvalues. That is the same eigenvalue solution some m times, right? So algebraic multiplicity is the power m of the term lambda minus b, right, of the characteristic polynomial. If you expand the polynomial as a product of a bunch of, right, say lambda minus some, I don't know, lambda I, at product of such terms, then some of the lambda i's are equal. Then that part of the product will be of the form lambda minus some b power m, right? So that m is called the multiplicity of the eigenvalue b, where our eigenvalue lambda equal to b. So if an eigenvalue lambda r has a multiplicity m, then for k really independent eigenvector associated with lambda r, one is less than k or less than equal to k or less than equal to m. So the problem is, in general, if you take a general square matrix, so which is not necessarily symmetric, then if you take an eigenvalue, let's say b of multiplicity m, the number of eigenvectors associated, linearly independent eigenvectors associated with lambda r, that particular lambda, need not be equal to m. It will be some value between 1 and m. Okay, so that value, let us say k. So if an eigenvalue has multiplicity of m, it can only have a number of eigenvectors equal to k, where k can be less than m. It need not be always equal to m. So therefore, in general, what happens is, for an n by n matrix, n by n real matrix, the number of eigenvalues is always equal to n, all right, but the number of eigenvectors can be less than n. Okay, so, all right, so in this case, if k is less than m, you say that such a matrix is called a defective matrix. That is, it doesn't have the full set of n eigenvectors. It has fewer than n eigenvectors, but it has equal to n eigenvalues. Right. So let's take this matrix, for example, A, B, 0, A. Let's try to find the eigenvectors and eigenvalues for this. We try to find the eigenvalues, solve this equation, determinant of A minus lambda B, 0, A minus lambda is equal to 0. You can see that lambda is equal to A, right? Two roots are the eigenvalues. These are two eigenvalues. That means m is equal to 2. So now let us try to find the eigenvectors. So plug lambda equal to A in this characteristic equation, in the eigenvalue equation. So you have A minus A, B is 0, A minus A, x1, x2 is equal to 0, because right, this characteristic, this equation, the eigenvalue equation, where you move both terms to the left side. When right term also you move to the left. So if you do that, you get this equation. So this means bx2 is equal to 0. The second equation is useless. All right, so bx equal to 0, so for x2 is equal to 0, and x1 can be anything. Okay, so which means if you take the normalized form, right, x1 can be any value, let's some non-zero value. So x1, x2 is equal to, let's say 1, 0 in normalized form. And that's the only eigenvector you can get, no matter what you do. Right, you cannot get any other eigenvector for this matrix, which means this matrix has two eigenvalues, A and A. That's a multiplicity of 2, but it has only one eigenvector. So such a matrix is called a defective matrix. Now, in general, a square non-symmetric matrix, right, can be defective, but a square symmetric matrix will always have n eigenvalues and n eigenvectors. It will never be defective. Right, and just to I'll give an example. That's a theorem. I'm not going to prove all the theorems. Right, I'll just state some of the results. But this property of multiplicity of eigenvalues is called degeneracy. Right, if a matrix has multiple eigenvalues, right, at the of same number, then it's that such a matrix is said to be such eigenvalue is said to be degenerate. So let's take this square matrix, a very simple matrix, only has diagonal terms, other terms are all zero. And you can also see it's symmetric, obviously, right? And that is Aij is equal to Aji. And if you calculate the eigenvalues of this, which is quite trivial, eigenvalues are 3, 3, and 5. So you see that eigenvalue 3 has multiplicity of 2. So it has 3 eigenvalues, but 2 of them are the same. So now if you so since 3 and 3 and 5 are the eigenvalues, right? If V is an eigenvector, right, BV is equal to 3V. This okay, so BV is equal to 3V and BW is equal to 3W. Let's say there are two eigenvalues, eigenvectors. So now from the linearity of matrix operations, we can combine this equation and say that B times AV plus BW, say A and B are some real numbers, right, is equal to A into BV plus B into capital BW, right? So BV is equal to 3V and BW is equal to 3W, right? So you get 3 into AV plus BW. So which means that if V and W are two vectors which satisfy this equation, two independent vectors, then any linear sum of them are also a solution. So therefore, even for this case where you have only one eigenvalue repeating twice, right? You can see that the whole subspace of vectors can be eigenvectors. So you can take any two independent vectors in that, right, and call them the eigenvectors corresponding to that eigenvalue, which is a degenerate eigenvalue. So basically, what happens is when the matrix is square symmetric, this is only an example, but the theory basically says that when the matrix is square symmetric, then you will have n eigenvalues definitely, and some of them are degenerate. Then for that set of degenerate eigenvalues, let's say of multiplicity m, you can construct, right, a set of independent system of independent eigenvectors of dimension m, okay, which span a subspace of dimension m. Then let us look at some of the properties of, right, symmetric and skew symmetric matrices. So just to define symmetric matrix, A is symmetric matrix if A transpose is equal to A. That is if Aij is equal to Aji if it is real matrix. If it is a complex matrix, then for a symmetric case, the definition is Aij is equal to Aji star, where star denotes a conjugate. So this is for real and this is for complex. So when a matrix is real and you call it a symmetric matrix, but the matrix is complex, you call the same thing a Hermitian, right? Which is given by this, defined by this condition. So where A is a complex matrix that is in C n by n. Now A is a skew Hermitian matrix if A transpose is equal to minus A or A star or the different notations, different books follow different notations. I'll just take A transpose for simplicity. So if A is a complex matrix, A transpose, we'll just assume that A transpose involves conjugation. So sometimes some books use the notation or terminology of transjugation, that which is transpose plus conjugation. So anyway, without confusing ourselves with too much terminology, we'll just like understand that transpose in case of a real is just this, right? But in case of complex case, you not only flip Aij and Aj terms, but you also do conjugation. So now let's look at a couple of theorems related to eigenvalues of Hermitian matrices or symmetric matrices if they're real. So the eigenvalues of a Hermitian matrix are real always. You will never have complex eigenvalues. Why is that? Let's start with the eigenvalue equation. Ax is equal to lambda x. Now multiply both sides by x transpose. You get x transpose x is equal to lambda x transpose x. Right? Lambda is scalar, so you can just take it out. Right, and so x transpose x is equal to lambda. X transpose x is just norm of x square, right? So now you transpose both sides of this equation at this point. So you get x transpose A transpose x. So you know that if you have three matrices A, B, C, and transpose, will be C transpose, B transpose, A transpose. So therefore, if you do that here, you get x transpose A transpose x, right, is equal to lambda star, which is conjugate of this, because transpose involves conjugation. And mod x square is a scalar, right? So, and a positive number. So it's a real number. So conjugate of that is still the same. So this is what we get on the right side. Now A transpose is equal to A because it's a symmetric matrix. So you have x transpose Ax is equal to lambda star norm x square. So basically, from this equation and this equation, you have lambda norm x square is equal to lambda star norm x square. Therefore, lambda is equal to lambda star, which means lambda is real. So this is the first result. So now if for the next case where A is Q symmetric, A transpose is equal to minus A, the theorem says that the eigenvalues of a Q symmetric matrix are purely imaginary. So how do you show that? Again, you start with the eigenvalue equation x equal to lambda x, multiply both sides with x transpose. So you get x transpose x is equal to lambda norm x square. So then again, like before, transpose both sides. You get x transpose x is equal to lambda star norm x square. Now A transpose is equal to minus A for a skew symmetric matrix or a skew Hermitian. So replace this with minus A here. So minus x transpose x is equal to this. So if you compare this equation and this equation, you get this, which means lambda is equal to minus lambda square, right? Which means obviously lambda is purely imaginary. Then we look at a third kind of a matrix, which we'll be using. This matrix we'll be using several times in the course. We'll call this the orthogonal matrix. That is, Q is an orthogonal matrix if Q transpose Q is equal to QQ transpose is equal to I. So it's first of all a square matrix, right? And it is its own inverse. That is, its transpose is its inverse. Okay, so therefore QQ transpose is equal to I, right? For such a matrix, for an orthogonal matrix, all the eigenvalues lambda, they have are of length equal to 1. Of magnitude is equal to 1. This is a complex number, right? And that means all the eigenvalues lie on the unit circle in the complex plane. So how do you show that? Again, start with the eigenvalue equation Qx is equal to lambda x, then take transpose on both sides. So x transpose Q transpose is equal to lambda star x transpose. So then multiply 1 and 2 equations. So you have x transpose Q transpose Qx is equal to lambda star x transpose. So lambda star and lambda you can take out, and x transpose x, right? So Q transpose Q is I, so therefore you can just knock off this part, and you have x transpose x is equal to lambda star x transpose x. Okay, so x transpose norm x square on both left and right get cancelled. You get mod lambda square is equal to 1. Okay, so therefore lambda is of the form some e power I theta. So all the lambdas sit on the unit circle. So if you summarize the three results and put them on a diagram, you can depict like this. For the symmetric matrix, all the eigenvalues are on the real axis. For the skew symmetric matrix or skew Hermitians, all the eigenvalues are on the imaginary axis, and for the orthogonal matrices, all eigenvalues are on the unit circle. So just to place them with respect to each other, relative to each other. Okay, so all the eigenvalues of distinct eigenvectors of distinct eigenvalues of a symmetric real matrix are orthogonal. So this is a proof. I mean, you can look at this later. Next, every symmetric matrix A that exists, for every symmetric matrix A, there exists an orthogonal matrix Q, right, such that Q transpose AQ is equal to diagonal matrix of all the eigenvalues, right? So, which means, let us say Qi are the eigenvectors. Qi is eigenvector of the eigenvalue lambda I, right? So, which means all the n eigenvalue equations can be written as AQi is equal to lambda I Qi, right? So then define a diagonal matrix D such that it has all the eigenvalues on the diagonal. Okay, so then you can easily see that. So Dij is equal to Qj transpose AQi. Why is that? If so, because AQi is nothing but lambda IQi. So therefore, you will have, right. So let me see this. So Qj transpose AQi is equal to Qj transpose. AQi is nothing but lambda IQi. So I can take lambda I out. So I get lambda I times Qj transpose Qi. So if all the eigenvectors are normal, right, to each other. So if j and I are unequal, then the dot product of Qj and Qi will be 0. They're equal, then it's 1. Right? So if I and j are equal, then this dot product is equal to lambda I. So if you look at this expression, otherwise it is 0. Therefore, you can, if you define the matrix capital Q as being composed of all the eigenvectors like this, Q1, Q2, Q3, they're all column vectors. Right? If you arrange them like this, then you'll simply have, if you just arrange them like that, you'll have an n by n matrix. And you can easily see by using this result here, Q transpose AQ is equal to this diagonal matrix, because that's what this theorem says. So now if you move things to the other side, right, move Q and Q transpose to the other side, you get A is equal to QD Q transpose. And if this expression, if you expand out in terms of individual eigenvectors and individual eigenvalues, you get A is equal to sigma lambda I Qi transpose. So note that Qi transpose is outer product of Qi and Qi. Oh, yes, Qi and Qi. Right, and so basically this you are decomposing A in terms of n outer product matrices, right? So Qi and Qi transpose is outer product matrix. There'll be n of them because there are n Qis, right? And then you can express the matrix A as a linear sum of n such matrices. So this kind of a decomposition of A is called the eigen decomposition of A. Next property. So one interesting property of an orthogonal matrices is the transformation defined by an orthogonal matrix is length preserving. What does it mean? So let's say I have y is equal to qx. So q, the multiplication by q transforms the vector x into vector y. And in this transformation, the lengths are preserved, which means norm of x is equal to norm of y. Why is that? Because take y equal to qx. So you have, if you take transpose of both sides, y transpose is equal to x transpose q transpose. Multiply these two equations, this and this. Then you have y transpose y is equal to x transpose qx. So q transpose q is I, so you knock it off. So you have norm of y square is equal to norm of x square. So lengths are preserved. So which means that multiplication by q simply rotates the vector, but doesn't change its length. Okay, so we have therefore looked at some very basic properties of matrices in terms of eigenvalues and eigenvectors. And we also looked at some important matrix classes, mainly symmetric matrix, skew symmetric matrix, and orthogonal matrix, and some properties of these matrices. Now let us look at another topic of linear algebra called the quadratic form, right? And we'll use this quite often, these ideas quite often in this course. So let us look at a few properties of quadratic forms. So a quadratic form is a quadratic function associated with a symmetric matrix A, and is expressed like this. So if A is a square symmetric matrix, or symmetric matrix which happens, this has to be a square matrix. Then the scalar function E, right? This is a function of x. Okay, so E is a function of x, the vector x is x transpose Ax. You can also put a half. Sometimes people put a half before. There's some, it doesn't matter. There's some nice algebraic conveniences. So, so this kind of functions arise in the study of, we'll look at neural networks and deep learning and all that later, right? You need this kind of a quadratic form idea later. So take a simple example. What is this expression? What does it look like? Let's take a simple case where x is two-dimensional. So x1, x2, and A is also 2 by 2 matrix. Call this A11, A12, A21, A22. Okay, so x transpose x, what is that? X transpose x is equal to x1, x2, A12, A22, sorry, A21, A22 times x1, x2. So you get x1, x2 times A11, x1 plus A12, x2 and A21, x1 plus A22, x2. So this is a column vector, this is a row vector. To multiply them again, you will have A11, x1 square plus A12, x1, x2 plus A21, x2, x1 plus A22, x2 square. So basically, if you, these two terms can be just added up. You get A11, x1 square plus A12 plus A21 into x1, x2 plus A22 into x2 square. So point is, no matter what the size of the matrix is, right, you will get this kind of an expression. So this is a quadratic expression, homogeneous, there are no linear terms. You might have encountered this expression in your high school coordinate geometry, right? If you take this expression, this kind of expression, and equal to, right, equal to z, equal to some constant, you get all these ellipses and parabolas and hyperbolas, right? And this is related to the whole topic of conic sections. So that is for n equal to 2, right? If you take this expression equal to, make it equal to some constant, a positive constant or negative constant, right, you get all these conic sections for various values of the coefficients. So it has lots of interesting properties. Now, why do we say that the quadratic form is related to only symmetric matrices? Because even for a non-symmetric matrix, let's say A12 is not equal to A21, I can always derive an expression, I get this. So the point is, you can easily see that no matter, even if whether, even when the two A12 and A21 are not the same, you are simply adding them up, right? So therefore, instead of the original matrix, right, suppose I considered, okay, instead of this, I consider like something like A11, A1, A2 plus A21 by 2, A21 plus A12 by 2, and A22. Against of this matrix, if I use this matrix, I get the exact same expression, right? So, so therefore, you may as well just study. This study has no relevance to non-symmetric matrices, right? Because in the expression, it is as though it's always symmetric. So therefore, we say that we'll study this only for symmetric matrices. Why is it relevant? So, thinking this kind of expressions. So we very often in the course we'll look at multivariate functions, right? Functions which are dependent on multiple variables. That's a multivariate function. And you want to find out the optima of this function. So where does it become maximum? Where does it become minimum? Things like that. So why do we need this? For example, we'll have to train a neural network and somehow find the weights which will minimize output error, right? And that output error is a scalar function, but it will depend upon all the weights, lots of weights, thousands and even millions of weights. So it's a huge multivariate function with a very high dimensionality. How do I define when it has gone to a minimum? What is the minimum of a multivariate function? Because we know what is the minimum of a univariate function, right? So like this, you have a function like this, I know what the minimum or maximum are, right? At the minimum or a maximum, you have first derivative is 0. Second derivative, if it is greater than 0, if it is positive, then you have a minimum. If second derivative is less than 0, you have maximum. So life is very simple if you have to determine the minimum and maximum of a univariate function. But you'll often deal with multivariate functions. So in a multivariate function, what is the second derivative, right? Because first derivative itself is a vector, right? So then what is the second derivative? It's not clear. Okay, so it is very easy to work out all these issues in the case of a multivariate function, because a quadratic form is basically equal to a quadratic function in a univariate case. Because basically, if I look at a function, I'm trying to find out the minimum or a maximum. I'm basically assuming that in the neighborhood of this minimum or a maximum, the function looks like a parabola. Why is that? Because if you take Taylor series, f of x is equal to some f of x naught plus x into f prime at 0 or x naught. Okay, or 0, let's keep it simple, plus x squared by 2 factorial, etc., and the cubic term, etc. So I just want to know if this function has a minimum or a maximum. Okay, so at that point, therefore, the first derivative is 0, so this becomes 0, right? And you have higher order terms, right? Now, whether this should be f double prime here, second derivative. So whether this function has a positive minimum or a maximum at this point simply depends on this quantity, right? And I don't need to know how are the higher order terms, right? So basically, I can truncate this expression at this point, and if I look at only this part, right, I can find out whether the function has a minimum or a maximum at this point 0. So the constant part doesn't matter because it will only lift the function up and down. Right, first derivative is 0, therefore the first linear term is gone. Now for the second derivative term, I'll just take only the up to the second derivative x squared term. If the coefficient is negative, the function will go down. If the coefficient is positive, function will go up. When the function goes down, it means it has a maximum. When the function goes up, right? If the function goes down to infinity like this, it has a maximum. If the function goes up to the positive infinity, it has a minimum at this point. It all depends upon the coefficient of the second order term. Okay, so basically we are approximating the function by a quadratic, by the test function f of x, by a quadratic function by truncating the Taylor series, and look at the coefficient of the second order term. This is how we are finding whether the function has a maximum or a minimum. Okay, this is the logic behind this whole idea of looking for the sign of second derivative and all that stuff. Now, all these ideas, how do we carry them over to a multivariate function? So for a multivariate function, now you need to extend the ideas of first derivative, second derivative, and all that. So how do you do that? So for a multivariate function, the first derivative now is also a vector. You have n derivatives. And how do you do that? So if the function is f of x1, x2, x up to xn, its a gradient, right, is defined, is mathematically given by this notation del of f with respect to x. The independent variable vector is x, is given by dou f by dou x1, comma dou f by dou x2, etc., and dou f by dou xn. So note that f is a multivariate function. Each of them is dependent on n variables or the vector x. Now, to calculate the second derivative, now second derivative is even more complicated because second derivative is not a vector, it's a matrix. Because second derivative means differentiating with respect to two variables. Now, since we have n variables, I'll have NC2 variable combinations to calculate second derivatives. So this second derivative becomes a matrix. They call it the Hessian, named after some guy called Hess. So Hij is equal to dou square, since it's a partial derivative, right? Dou square f by dou xi dou xj. So for this, in the case of a multivariate function, a second derivative is a matrix called a Hessian. And why do you need this kind of derivatives? Because to find out whether a function has a minimum or a maximum, if it's a multivariate function, right, you need to expand this out in a Taylor series form, and then look at what's happening with the second order term. Then we'll ignore the higher order terms. So what is the Taylor series for a multivariate function? Because we know the Taylor series for a univariate function, which itself is somewhat complicated. But how do you find the Taylor series for a multivariate function? So let us see that. So I'm looking at a point x naught in the input space, and I want to see around that x naught does the function have minimum or a maximum. I'll assume that at x naught the gradient is 0, because that's when it's interesting. Otherwise, there's no minimum or a maximum. So I expand this function f of x naught plus h. H is a deviation from x naught. So you have f of x naught plus. So what do you do? X is a deviation. So g is the first derivative. So h transpose g is a linear term. Now the second order term is where you get h transpose capital H times small h. Okay, so this term is equivalent to this term. Second derivative times x squared by 2 factorial, right? That's the second order term. Equivalent of this for the multivariate case is this 1 by 2 factorial into so it's not right, small h transpose times h times small h. So this is your quadratic form. So this is how the quadratic form idea becomes useful if you want to understand whether a multivariate function has minimum or a maximum. Because to understand minimum or a maximum for a univariate function, we approximate that function around a potential minimum or a maximum by a quadratic function, right? So the quadratic function for multivariate case is quadratic form. Okay, so you see that. So since g equal to 0, we can capital G is equal to 0, derivative is 0. We can ignore the linear term. Now higher order terms beyond quadratic or let's say are too small, and we ignore them. So function f of fx has a minimum at x naught if the function 1 by 2 factorial h transpose capital H small h, right, has a minimum at h equal to 0. Okay, so does it have a minimum at h equal to 0? Right? Well, what is the shape of this function? Right. So the point is the shape of the function that we are studying, f of x, right, around a point x naught, where at x naught the derivative is 0. It all depends now, it reduces to the shape of this quadratic expression. Okay, so the bigger problem is now reduced to a more specific tractable problem. Right, and now we have to answer it, does it have a minimum, does it have a maximum, and does it have something else also? Because even in univariate case, you may not always have only maximum or minimum, because I don't know, you never study this, maybe you may not have paid attention to this. because look at this function. This has a maximum f prime is equal to 0. This has a minimum f prime is equal to 0. You can have functions where derivative is 0, but it's neither a maximum or a minimum. Right? F prime is equal to 0. So this is a max. This is a min. This is neither. So this happens when, for example, y equal to x cubed. So not only first derivative, second derivative is also 0. So it gets very messy. Okay, so these, even in univariate case, the question of min max is somewhat tricky. Right? In multivariate case also it is even worse. So we'll take a break now, and we'll discuss in the next class how do you understand the shape of this expression, this quadratic form, right, involving a matrix H, capital H, right, and a vector small h. So in our case, in more general terms, x transpose Ax. What is the shape of this function around the origin? Okay, well, what is it? Because everything is inside the matrix A. It's a matrix A determines all the coefficients of this expression. So the shape of this function depends on the elements of A, but exactly how? Okay, so let us take up that question in the next class, that is tomorrow.